Okay, the next topic on our agenda is imitation learning. We'll see how to train a policy to imitate either demonstrations or a specific demonstrator, but not necessarily with reward function. I mean, we'll see one situation where we can actually reduce imitation learning to reinforcement learning, but in the general case, there's no reward function, just demonstrations or a demonstrating policy. We'll discuss all of those. So the high-level problem that we're trying to solve here is that given some demonstrations or a demonstration, so demonstrations in a specific environment will be the output of the controller in some states, or we'll either assume that we are getting demonstrations, states, and then the action that should be taken at those states, or a demonstrator will actually be given not the control function of the demonstrator, but will be able to ask the demonstrators for an action given any states that we decide on, right? So we won't assume to have access to the internal logic of the demonstrator, but we will assume to be able to query the demonstrator. So that's, for instance, it can be a human demonstrator, right? Maybe a human driver where an autonomous car is trying to learn from the human driver. We don't have access to the human's brain, but we can ask the human, hey, what should we do in this situation or that situation? In any case, our goal is to train a policy that would imitate the demonstrator as closely as possible. Can we imitate the demonstrator perfectly? Can we?
Approximately?
Not always, right? We have some approximation limitation. So our approximator is usually limited in its ability to represent policies. By the way, we also need to assume that the demonstrator is not ambiguous. If it's ambiguous, then I'm not even sure how to. Maybe we need more features, right? So, in generally, we won't be able to perfectly imitate or train a policy that perfectly imitates the demonstrator, but under the approximation limitation, within the approximation space, we can find the best fitting approximation assignment, right? The best approximator under our assumptions. So in the general case, we have the X for demonstration, we have the state action pairs, and these can be either set, right, with a set of demonstrations, or these can be interactive, that is, we can query specific states for their action. And then we'll need to use those demonstrations in order to train a control function. It can be a deep neural network, it doesn't have to be a deep neural network, right? We can do it for any approximators, most approximators. Specifically, actually, some of the solutions that we'll later see assume a specific demonstrator. It's usually any differentiable approximator would work. Okay, moving on. What are the ingredients of imitation learning? What do we need in order to perform imitation learning? So we need the demonstrations or a demonstrator. We need the environment, access to the environment, right? We need to somehow interact with the environment in an online way. Next, we'll need a policy class, hopefully a differentiable one. We'll see even one solution that requires a linear approximator. Then we'll need to define a loss function. What do we mean? What does it mean to perfectly or to imitate more closely the demonstrator and less so, right? The loss function can tell us that, how good we are imitating the demonstrator. More than that, right, we need to compute, what will we need to compute with respect to the loss function?
The gradient.
The gradient, right. We need to compute how to change our output, our control function, such that the loss is reduced. So we need a differentiable loss function. And finally, we need the learning algorithm. So again, if we're going with the differentiable loss function and a differentiable policy, commonly we'll use
DBO?
No, gradient descent,
Okay.
gradient updates. You can use PPO, we can use other algorithms.
Learning a policy. So.
Okay, but any gradient based approach should work. That's mostly what we're going to use. Okay. So let's see a short video explaining the imitation learning problem. This is by OpenAI, as you can see.
Infants are born with the ability to imitate what other people do. Here, a 10-minute-old newborn sees another person stick their tongue out for the first time. In response, he sticks his own tongue out. Imitation allows humans to learn new behaviors rapidly. We would like our robots to be able to learn this way too. We've built a proof-of-concept system trained entirely in simulation. We teach the robot a new task by demonstrating how to assemble block towers in a particular way, which in this case is a single stack of 6 virtual blocks. Previously, the robot has seen other examples of manipulating blocks, but not this particular one. Our robot has now learned to perform the task, even though its movements have to be different from the ones in the demonstration. With a single demonstration of the task, we can replicate it in a number of different initial conditions. Teaching the robot how to build a different block arrangement requires only a single additional demonstration. Here's how our system works. The robot perceives the environment with its camera and manipulates the blocks with its arm. At its core, there are 2 neural networks working together. The camera image is first processed by the vision network. Then, based on the recorded demonstration, the imitation network figures out what action to take next. Our vision network is a deep neural net that takes a camera image and determines the position of the blocks relative to the robot. To train the network, we use only simulated data using domain randomization to learn a robust vision model.
We already saw domain randomization.
We generate thousands of different object locations, light settings, and surface textures, and show these examples to the network. After training, the network can find the blocks in the physical world, even though it's never seen images from a real camera before. Now that we know the location of the blocks, the imitation network takes over. Its goal is to mimic the tasks shown by the demonstrator. This neural net is trained to predict what action the demonstrator would have taken in the same situation. On its own, it has learned to scan through the demonstration and pay attention to the relevant frames that tell it what to do next. Nothing in our technique is specific to blocks. This system is an early prototype that will form the backbone of the general-purpose robotic systems we're developing here at OpenAI.
Okay, so actually the main point that I wanted you guys to take from this video is what the demonstrator here, the person demonstrator, I don't want to overload the term demonstrator, is what they said at the beginning, what he said at the beginning, when he said it helps us learn rapidly. And this is the main point here. So the test that you just saw with the stack blocking by the robot arm manipulator, that's not a very difficult test. That is a reinforcement learning agent can learn this task and can learn it pretty effectively. Pretty effectively, that is to perform the task pretty effectively. But the learning itself will take time, right? It will require a lot of samples and a lot of interaction with the environment, where with imitation learning, we can really speed up the learning process, okay? And indeed, this is mainly what we're trying to do when we combine imitation learning. By the way, we can combine imitation learning with reinforcement learning, do some initial steps or initial training with imitation learning, and then fine-tune using RL. Okay? But imitation learning can, specifically in complex tasks, can help a lot in speeding the initial training.